We will study now how to calculate the sampling size, so the sample size n, taking into account that we can stop early the experiment. This is a very interesting approach that is very much used in clinical trials because of their cost and also because we are using humans, and then we are much more careful about them, and not so much used in animal research, although we could save a lot of animal lives using this. The problem is that the statistical tools used to analyze the data and to design the experiment are much more sophisticated. We will address three different problems. So in the first one, we will use only one sample and study what is the proportion of respondents to the drug. In the second one, in the second group, we will compare two samples, and we will compare them at different levels, so different means, different proportions, different hazards. And in the last case, we will re-estimate the sample size. So in the middle of the experiment, we will recalculate the sample size that we need. And yeah, so let's start with the first group. So the first group is the superiority of a proportion. So let's say that you are in a phase 2 clinical trial whose goal is to determine whether a new drug produces a sufficiently high response. And we plan to do a two-stage experiment. So we will divide the individuals in two parts, and then after the first part, we will take a decision. The first mini experiment, we will take a decision whether to go on with the experiment or not. And we want to have, so we will stop the experiment if the probability of responding is less than 5%, and we want to have a statistical power of 90% or whatever percentage if the probability of responding is larger than 25, let's say. So there is a test of this kind, and the key thing is that we will perform a test, an intermediate test. So how do we design the sample size in this case? Okay, so for doing this, we have to analyze both stages. So let N1 be the number of patients in the first stage, and let us call R1 the maximum number of responding patients in the first stage. And if we don't have more than R1 responders, then we don't go into the second stage. Okay, so let's say that the true proportion of responding patients is P1. P1 is the one 25%, so the high one, the one at which we want to have the statistical power. And then the probability of termination after stage 1 is the probability that the number of responders is smaller or equal capital R1. This is a binomial distribution, and this sum has to be smaller than the statistical power. On the contrary, we will continue with the experiment. So let's say that the null hypothesis is true. So if the null hypothesis is true, then we have a low number of responders, that is P0. And then we will continue with the experiment if we see R1 or more, R1 plus 1 or more responders. So again, this is a sum of a binomial, and this has to be smaller than alpha. So these are the typical sample size calculations that we have seen when we were designing for proportions. Okay, now let's consider the first and the second stage. So let us denote as R the total number of respondents, including both stages. And then we will decide whether to go to phase 3 clinical trial. So we are now in phase 2. So let N2 be the number of patients in the second stage. So the total probability of rejection of the drug if the drug is useful is this one. So the probability of termination in stage 1 plus the probability of termination in stage 2, that is calculated in this way. And this has to be smaller than the statistical power. And on the contrary, if the reality, so if the null hypothesis is true, so P, the number of respondents is P0, then the probability of making a type 1 mistake, having a false positive, is the probability of continuation in stage 1, that is this one that we have calculated here, and then times this thing, and this has to be smaller than alpha. Okay, so we have to find n1 and n2 such that for given p0 and p1, these two inequalities hold, these two and these two. So we have to find n1 and n2 so such that this holds and this holds. And there are two kind of designs. In the first one, we minimize the average number of individuals. So what is the average number? So it is n1 plus n2, but n2 doesn't enter fully, because if we terminate the experiment, we don't have n2. So this probability multiplication in front accounts for the fact that we don't always go into the second stage. So we want to minimize the average number of individuals, subject to that we have the statistical power that we want and the confidence level that we want. Or we may minimize the total number of individuals. This is called the maximum number of individuals. So the maximum number of individuals that we will have is the n1 plus n2, and again we are subjected to this. So the solution to these problems are given in the next slide. So you may use a computer to compute them, but there are also some table, and in the next table they have used a different notation. So PT1, so the probability of termination in stage 1, they have called it probability of early termination. En in the table is the expected number of that is the average or the maximum number, so this n1 plus n2 depending on the design. R1 is our capital R1 and R is our capital R. So this is the table. So in this table what we see is that, for instance, our experiment, that was this one, so we had P0 5%, P1 25%, depending on what is P0 P1, then you go to a different entry. Okay, so let's see. So our experiment was the first row, so the first row, this one, so we have R1, N1, R, N, and so on. So let's interpret it. Okay, so in the first stage we have R10, N1, 9. This is this entry here. So we have 0 and 9. And in the second stage we have 2 and 24. So we have 2 and 24. Okay, so that is, we will reject the drug in the first stage if we do not observe any response between 9 patients. This is 0 and 9. So you test your drug. If you don't see any response in 9 patients, then you stop it, because you assume that you have a very low proportion of respondents. If there is one or more responses, so more than R1, then we go to stage 2. So now you go to stage 2, and if there are 2 or less responses amongst the total of 24, then you reject your drug. In the second stage, you don't study 24 people, you study 15 people because you already have 9. And in this design, the probability of terminating in the first stage, if the null hypothesis is true, is 63. This is this probability here. And the average number, or the expected number of patients to study is 14. So you have a design that uses 9 or 24 patients. So 9 if you stop early, 24 if you don't stop early. The average number of patients is 14, so you have lowered from 24 to 14 because many cases, if the null hypothesis is true, you don't go into the second stage. So it is a very useful design. We can also complicate it a bit more. So what if we have more stages? So we can try to answer the following question. So let's say that we have observed in the first N1 patients, we have observed R1 responses. What is the probability that less than C responses would be observed in the N patients, including the first ones? Okay, so this probability is called the predictive probability, and we need to assume what is the proportion of responders that we will call P, and this P follows a beta distribution with A and B parameters that we will learn how to compute, and then the probability of observing exactly R responders in N, having observed R1 in N1, is this one. It looks complicated, and the predictive probability is the sum of many of these kind of probabilities from R1 to C. Okay, so what is A and B? So A and B, we need to assume what is the proportion of responders. So let's say that it is P0, so let's say it is 10%, and we have to say what is the proportion, the coefficient of variation, that we will call it V. So this proportion of variation is how much uncertainty we have around this P0. So then given A and so V and P0, we can calculate A and B. Okay, so for instance here we have a few examples. So let's say that these theta, the probability of response, and this is the prior coefficient of variation, and then we have A and B, and then we have some examples about let's say that we have in N1 patients how many N1 was 10. We have observed R1 responders. What are the probability that we observe at least 3 in a full sample size of 25? And then we have here these predictive probabilities that are these ones here. Okay, then we will divide our full experiment into case stages, and for each one of the case stages we will have N1, N2, Nk individuals. The trial is terminated if at the end of each stage the predictive probability exceeds a value P0, capital P0. So we need to calculate Ci that are called critical numbers, such that if the number of cumulated respondents until the stage I, that is called Ri, is smaller than this, then the trial is terminated. And then we can calculate all these probabilities. So for instance, what is the probability of observing R respondents in the stage I, assuming that the proportion of respondents is this one, is a binomial, and the probability of having a cumulated number of respondents of Ri up to the stage I is the sum of these kind of things. So these are so the design, you can see it is much more complicated, and we can compute the significance, we can compute the power, and you see that there are different significances, one at each one of the different stages. So each stage has its own significance, and we have the total significance, that is the sum of all of them, and the same for the power. So calculations are much more complicated, but what we see is that we can design the experiments in very kind of creative ways. So for instance here, so let's say that we have only one stage, or two stages, or three stages, four stages. Then we are assuming that we have a probability of respondent of 30%. We want to have a minimum predictive probability for early termination of 0.85, and then for instance here, this is the sample size that we want in total. So in total we will use 25 individuals, but depending on whether we use a single stage or multiple stages, then we for instance, for a single stage we use the 25, and we have a critical value of 3. So if we don't see at least 3 respondents in the first stage, that is the only one, then we reject our drug, because it has a very low proportion of respondents. But let's say that we divide it in 2 stages. So then in the first stage we will have 10, in total we will have 25. So if in the first stage we see 0 respondents, then we stop, and then in 25 we have to see 3. Or we can divide it into 3 stages, and then we have 19, 17 and 25 in total, and then the number of the critical value are 0, 1 and 3. Or we can divide them into 4 stages, for instance, so 6, 12, 18 and 25, and then these are the numbers, the critical values. So yeah, you can see that you can lower quite a lot the number of samples that you analyze, but it is true that the design is much more difficult, and the analysis is also much more difficult. Well, the analysis is not difficult in the sense that you have to compare only the number of respondents to the critical values, but the calculation of those critical values at the design stage, they are more difficult. Okay, so let's stop this video here. So we have seen how to divide the experiment into mini experiments, and then we can take decisions earlier in the experiment if we see that our drug is not very effective. So let's stop it here.